Hello everyone, my name is Paige Tian. Today I would like to present you my project on a computer vision deep learning method for the detection and recognition of manual window openings for effective operations of HVAC systems in buildings. I am currently a PhD researcher at the University of Nottingham. My interest lies within the use of AI and building energy systems. This shows an outline of the areas which will be covered in today's presentation. As we all know, significant amounts of energy are used by buildings, which results in today's consequences. Additionally, HVAC systems are the main part required to keep a building functioning. Therefore, the development of energy-efficient techniques are required to help minimize losses associated with building systems. There are many types of occupancy behavior which affects building operations. One is the opening and closing of windows. This is one of the most common natural ventilation strategy, which is employed within most buildings, especially within the UK. However, due to occupancy actions, windows can be easily left open. This results in greater amounts of ventilation losses, which would generally lead to greater amounts of energy usage. AI techniques such as deep learning performs a repeatedly classification task directly from input data of images, text or sound. It outperforms traditional learning algorithms. This includes machine learning through the use of neural networks. The following images shows examples of deep learning classifications. Existing window detection-based solutions were intended to cope with future developments through sensors that are connected to building energy management systems. However, given by these two solutions, limitations occur within these designs. This includes the requirement of sensors to be installed on every single window or existing windows to be replaced by automated windows. Therefore, through previous studies and solutions, it indicates the importance of occupancy behavior towards window openings on the impact of building energy performance, energy management, and also the indoor environmental conditions. Therefore, there is a need for more advanced AI deep learning-based approaches to aid buildings to work for future needs. Currently, there is no application that consists of the combination of deep learning with window recognition to aid building and energy management. This project aims to develop a deep learning-based window detection approach to enable the notification for occupants as well as data for building control systems to effectively manage building system operations while providing better thermal conditions for the desired space. The objectives include the following. The next following slides will present the methodology used. The method is consisted by the 7 steps. Steps 1 and 2 are the initial steps for developing the deep learning model for window detection. Deep learning profiles are formed from live detection of window conditions, and the data is given to step 4 to inform occupants and systems controls. Additionally, steps 5 to 7 were used to enable the analysis of the developed approach based on building energy performances. This shows the images of closed and opened windows, which were collected and labeled as the selected response outcome. It formed the initial part of the deep learning model process, where TensorFlow was used to train a deep learning CNN model to perform real-time detection. Part 1 consists of the data analysis and the development of the deep learning model. Part 2 consists of utilizing the trained model to provide live detection and recognition. A CNN image-based neural network was selected to train the deep learning model. This shows the architecture of the developed CNN. The network is based on the transfer learning approach using the TensorFlow Object Detection API. Also, to achieve higher accurate detection, a pre-existing trained model, such as the faster RCNN with Inception v2 was used. lecture room within the Marmont Centre at the University of Nottingham was used as the initial test room and was also modelled as the case study building for building energy analysis. This shows the setup with the south-facing window 1. To assess the deep learning-based approach using building energy simulation, an initial 2-hour detection within the case study building was performed. This was along with the use of the window and building conditions assigned to the case study building in the building energy simulation. This shows the process in which data of the detected and recognized windows were recorded in terms of a deep learning influence profile for each of the windows A, B, C, and D. The following presents the results and the corresponding discussion from the analysis of the developed approach. In reality, the window detection and recognition results, which form the occupancy profiles, would directly feed to notify occupants about the window conditions and also the building control system to monitor HVAC systems. However, for analysis, the deep learning window profile results will feed into the created building energy simulation cases to perform building energy performance analysis. For the developed CNN model, the following shows the training performance. The convergence of the loss functions implies the model has been effectively trained. Here shows an example of the real-time window detection of windows being opened and closed within the case study building. Accurate detection for each window can be shown. However, there are still errors in detection, which shows further development are required to achieve higher accuracy. Test was performed within the selected lecture room with various combinations of window openings on window A to D. The corresponding deep learning profiles were plotted here against the actual window conditions. The accuracy of the real-time detection is shown here. Effectively, an average accuracy of 77 was achieved, the highest with window A achieving 89.2% on detecting being closed and window D for being opened with 90.3%. This detection is solely based on the specific location, time, and environmental conditions. Within current building HVAC system operations and building energy simulations, windows are usually assumed to be closed or opened following these typical profiles. This is different compared to the actual observation conditions and the ones formed by the detection. This results in the differences between the obtained building heating performance, where the typical constant profiles of windows cannot represent the conditions to provide accurate building heating loads. Similar to heating, ventilation losses achieved in the lecture room is highly dependent on the conditions of windows. Therefore, this shows the importance of needing this approach to recognize the conditions of windows for a better understanding of the true building requirements. In conclusion, we have developed an initial demand-driven, deep learning-based framework for the detection and recognition of windows. The current model provides initial average window detection accuracy of 77.78%. The use of constant static scheduled window profiles are not sufficient for effective HVAC system designs and building energy performance evaluations. Therefore, the ability of this deep learning detection to inform HVAC systems will significantly help towards reducing building energy loads. Therefore, it is important to require an effective real-time window detection solution to assist building energy performances. The future works of this project includes the enable of the detection and recognition to effectively work under the following conditions. This includes for different types of window designs, when windows are obstructed, and under different building indoor and outdoor conditions. Furthermore, we intend to integrate this window detection model with our other occupancy activity detection model to enable accurate HVAC adjustments based on occupancy behavior within buildings. Thank you for listening. I hope you enjoyed my presentation. I am open to any of your questions.